Hello, everyone. Our last classes were quite complicated, so I decided to try to discuss them again calmly. That's why, for the sake of shorter classes, I created a series of videos that I will upload here for you. I hope they will be helpful. And if you have any questions, I am here for answering it, and please feel free to ask them. Okay. Dear students, our recent class were about designing railway lines on the map and selecting specific design parameters. As I told you in the classes, our requirements were based primarily on the subject of the designing classes I gave you. On the other hand, most of the input parameters can be selected by you depending on what kind of railway infrastructure managers we have in Poland, in the world, or in your country in which the railway infrastructure will be designed. If there will no such guidelines, then there are also a technical specifications of interoperability, the TSI, as a starting point. And as a part of this document, certain key parameters are defined, such as gauge, such as axle load, such as length of the train, maximum speed, or even the usable length of the platform. As I showed you at the classes, these parameters are defined directly in several tables. They concern both parameters of passenger trains, an example for the passenger traffic, as well as for the freight trains or the freight traffic. Now you can see the passenger traffic, yes, and the traffic codes. And here you can see the parameters for freight traffic, as the traffic codes and all of the characteristic parameters. As I said, during the class, we will be using the parameters defined in the subject of design exercises, and then we will design our entire railway line based on the EN 13803 standard, which I have already explained to you in the last classes. But let's do it once again, more precisely and a little bit slower. First of all, here are few key definitions which I will not explain in detail. You can read by yourself. Or if there is need, I will explain them in the separate video. Please inform me if you want a video of these definitions and their explanations. However, after the definitions, we can go directly to the parameters that we will be counting for our railway line. Before we start the calculations, I would like us to understand that in the framework of designing a railway, there are three types of alignment elements depending on the surface of the railway line. First of all, we have elements related to the horizontal alignment. Here we are talking about the straight sections, lines, about circular curves, transition curves, clotoid type, and other types. These four basic elements, and in fact three, allow for the design of a railway road on the plane, in this video precisely in the horizontal alignment. The second group of the elements are elements for the vertical alignment. And here we already have two types of the section. We have section with a constant slope, in example straight section with a constant gradient. And we have a vertical curves, parabola, or circular type. The third group of elements is the elements associated with the cant. We have the constant cant, linear cant transition, and can transition with non-linear transition, in example, the sinusoid without transition. If we have explained some key elements of our railway line, we can go directly to determining the key technical parameters. The EN standards allow us to estimate the radius of the part of the horizontal cycle, the circular curve. The minimum, the lower limit radius value, is 150 meters. Next, the standard specifies the normal maximum value of possible Kant limit. Here we have a typical value of 160 mm and exceptional limit value of 180 mm. You will basically take the 160 mm as the typical limit value. However, in exceptional situations, in example on crossing and switches, these values are reduced to the value of 120 mm or 160 mm in exceptional limit. If we have estimated the lower values of the radius, the minimum and the upper value of the Kant, then we have to start calculating the key operation parameter, which is the Kant deficiency I. The misspelling of the letter I is defined by a specific equation. This equation consists of a few parameters that need to be defined. Here we have, among the other things, the maximum speed V. We have the radius of our curve R, which you define by yourself. We have also our Kant D, and we have the QE parameter, which in our case is 11.8. And now we have to refer to the upper values of the Kant deficiency. In our case, because you will have a design speed of less than 200 kilometers per hour, the limit is 153 millimeters. So now, in short, for the set of parameters of speed, radius, and slope, Kant, you check the choice of Kant deficiency and you compare it to the maximum value, the normal limit. If the value of calculated Kant deficiency is within the range, you can assume that the radius of your curve and the Kant have been designed correctly. The second parameter that we have to calculate is Kant excess E. As a rule, the value of the excess is the opposite value of the Kant deficiency I. However, if we want to estimate the value of the excess precisely, we can use the proper formula. On the basis of this formula, this equation, we estimate the value of the excess of the Kant for our assumed value of the Kant and the previous value horizontal curve, the circular curve. Next, we compare the value to the upper limit. In our case, the standard upper value is 110 millimeters. If the calculated value of the Kant excess is less than 110 millimeters, then in the case we can safely say that the radius and the Kant have been selected correctly. Of course, taking account these two parameters. Finally, we need to calculate the change in Kant, which is nothing more than the change in Kant along to the length of the transition curve. The transition curve will be explained in the last lesson. However, now we need to include it in our calculations. For this purpose, we assume a certain length of the transition curve. In example, L is equal 100 meters. And for this length, we calculate the change in Kant, the Kant gradient. If the Kant is about 120 millimeters, then the Kant gradient is 1.2 millimeters per meters. Then the table 12 applies, which proposes the limits for the change in the Kant gradient. If the calculated value is less than 2.5 millimeters per meters, then the cant and the transition curve parameters have been selected correctly. If the cant deficiency and the cant excess for our assumed parameters of the radius R and the cant D for our horizontal alignments has been selected correctly, then we can start tracing our railway line in the map. So we can go now to our design algorithm. The route of our railway line consists of connecting 2 points that you have marked on the map. I will explain it to you in a separate video, but here you can create an algorithm that you can use for your work. In the first place, you assume a certain value of radius R, which must be less than 150 meters and must be also large enough for your assumed technical and operational parameters. Here, I suggest that there will be a value of, for example, 1000, 1500, 2000, or even 3000 meters. Further, based on the assumed value of the radius, we set the tangent for the arc and calculate other additional values. Next, you take a certain value of D, let it be between 20 and 160 millimeters, and you calculate two basic parameters, the cant deficiency and cant excess for your defined cant and radius value. Both values, I and E, are related to the value 153 millimeters and 110 millimeters maximum allowed limits. If the values of the parameter I and E for the values of the radius R and cant D defined by you are in the limits, then you can assume that the radius and the cant are proper. And at the very end, you calculate the cant gradient. This change is set by setting the length of the curve of the cant run. You can also use the example which I showed you a few slides before. Also, you assume the minimum length of the straight line between the curves. It is calculated individually for every situation, but let's assume for the sake of our classes that it will be minimum 50 meters. And if all of these parameters are approved, we can start tracing the line of the map. The route must be designed between the starting and ending point. Firstly, you propose that both points are connected with some straight section, some straight lines. Our task is to design appropriate curves in the bends of these straight lines. The circular curves must be selected based on the parameters of cant and radius that you have calculated. If this is done based on your calculations, we can assume that the railway line route horizontal alignment has been designed correctly in reference to the EN 13803 standard. So that's all. Further, I will show you how to implement the whole project along with the proper calculations and proper conditions for the project in the AutoCAD Civil in the other videos. Please look forward for it. That's all for me now. Thank you very much. And if you have any questions, please free to ask. Goodbye.